Hello, my name is Sean Jordan, and I'm presenting Physics 2212, Lab 3, Magnetic Field of a Bar Magnet. The glow script and spreadsheet data will be in the description below. Alright, so the purpose of this lab is to measure the distance dependence of the magnetic field of a small bar magnet. And we will be doing this in a physical experiment and then inputting the data we get from that experiment into a computational model. The main fundamental principle that we use in this lab is the Savart law. So the objectives of this lab are to first measure and record the magnetic field on and off the axis of the magnet by the magnetometer, which is the phone, and then inputting our data into a spreadsheet to then calculate a linearization of our data based on the distance dependence. And finally, we will be expecting to see a magnetic moment visualized in our computational model. The system for this experiment will be the magnet itself, and then the surroundings will be everything else. Here you can see all the main equations we will be needing for this experiment. First, we have the Savart law, or formula, to calculate the magnetic field, the distance dependence formula, and then finally we have our linearization formula. This is the setup for the experiment, with the linearization calculation being part 1 and then the off-axis calculation being in part 2. First, we will download a magnetometer app on our phone, and this will be able to basically see where and how much the magnetic field is at based on our phone's location. In this experiment, I used an iPhone 14, and the chip was located in the lower third of the phone, just to make it more accurate. Next, after setting up the measuring stick with our magnet, we will slowly move the phone closer to the magnet, and then put in our readings into the spreadsheet. For the perpendicular magnetic reading, we will be utilizing a location Earth. So I use the magnetic field from Atlanta because that's where I'm taking the calculations from. Here is the spreadsheet data that was gathered after conducting the experiment. The table on the left shows the on-axis data that was gathered, including the magnetic field reading and how far away it was from the chip. And each reading also has 3 trials, just to make it more accurate. After inputting this data, it yields a graph shown on the right, which gives a linearization of the data in the y equals mx plus b formatting. And this will be useful later when we're calculating certain variables. Finally, the table on the bottom shows the off-axis dperp data, which is gathered using the net magnetic field. The perpendicular average, circled in red at the bottom left, will also be useful, as this is important for the coding section. Here are the calculations to find mu, or the magnetic moment. We first use the linearization formula and associate that formula to the observed calculations from our data. As you can see, n is the slope, x is the natural log of the distance, and the intercept is the natural log of k. In order to find just k, we simply take the inverse log of the y-intercept, which yields the value 9.338 e to the -7. Next, we need to associate the distance dependence formula to the Savart law. We can do this by simply equating them to each other, since the magnitudes of the Savart formula equate to the distance dependence formula. After some rearranging and plugging in, we come to the magnetic moment of 4.669 amps per meter squared. Here's the initial conditions for the computational model, where we simply create a function of calculating the dipole moment and plug in the magnetic moment that we found in the last slide for mu mag. Here's the code for the visuals, which we utilize the dperp found from the spreadsheet calculation earlier to find the distance and magnitude of the magnetic field at our given observation location, and in this case it's at 45 degrees. Potential errors for this experiment are inaccuracies when retrieving the data from the magnetometer app and rounding errors when inputting these values into the spreadsheet. Here's some observations that we may or may not see in our experiment. You can pause here if you want to read them in greater detail. Out of these possible observations, 1 and 4 are the only ones that were seen from the experiment itself. What if you had not orientated the experiment to compensate for the magnetic north? Well, this wouldn't change much on a grander scale. However, on the mini experiment that we're dealing with here, it would make calculations much more difficult, as we would have to introduce angles. Also, if we were not moving the magnet at all with our angled experiment, This would make the magnetometer readings much more inaccurate. Now, what if you stuck two mags together? How would that change the measurements? Well, it would change the setup. It wouldn't change the setup much at all, but it would most likely increase the scale of our measurements, as the combined magnetic fields would cause it to be stronger, therefore introducing a higher scaled magnetic reading for all of our values that we found in the spreadsheet. That is the end of this presentation. Thank you for listening.